Much of the preliminary design, development, and building of the CF-105 is now well underway. One important phase of the work is the building of functional mock-ups and models. Under the supervision of the senior design engineers, the full-scale fuselage mock-up has quickly taken shape so that it will be ready to serve a most useful function as the design and building programs move ahead. It has largely been built by direct layout on vinylite, the lines of which were manually transferred to the wood, which has been used for nearly all components. It will serve an increasingly useful function in many ways. The cockpit will be fully outfitted. The positioning of equipment can be determined or checked in the fuselage, and problems can be sorted out concerning the installation of hydraulic lines, air ducts, electrics, radar, and the engine installation. Position and operation of controls can be determined. Built through the summer, fall, and winter of 1954, the fuselage will be virtually complete in every detail, even down to the application of the skin, which, as we see in this case, is made of thin sheets of plywood cut to the proper size and shape and fastened over the stringers, formers, and bulkheads. The same amount of skill and care must go into the building of this model as will go into the production aircraft, since the final determination of the position and function of many parts and accessories in the production models will depend on the manner in which they are finally installed in the mock-up. Some idea of the vast array of electronic equipment necessary to the operation of an aircraft of this type can be gained from the amount of wiring here being installed in just one of the many locations which will be heavily wired. In this case, the installation being completed is in the armament bay. From the tail end, this huge tunnel we see will eventually house the air intake ducts, the engines, and the jet pipes. From the mock-up of these details, we will learn much about their installation, and we will determine the ease of servicing or replacing them. At the intake end, the details of the intake ramp and the boundary layer bleed between the ramp and the fuselage have been completed, and the details of the cockpits and the canopies are gradually taking shape. One of the more important functions of the mock-up is the evaluation by RCAF personnel. Through the use of detailed question sheets, a variety of opinions can be analyzed and many ideas can be examined. Much can be learned regarding the function and accessibility of cockpit controls, instruments, and switches, and many more details which will be important to the men who eventually will fly, service, and maintain this aircraft. Because of its size and method of operation, the main undercarriage presents a major problem. This quarter-scale model is fully operative and is helping to solve the problem. This version of the original single-seat cockpit, built in late 1953, sorted out many of the early problems concerning instrument layout and windscreen and canopy design. The design requirement for a V-shaped windscreen brought with it a handicap. A serious reflection problem became quite evident when the cockpit, mounted on a truck in normal taxiing or takeoff attitudes, was driven down the runway. A series of interesting but undesirable patterns paraded continually across the windscreen whenever the unit was moving. A narrow shield was then devised and installed in the V between the two sections of the windscreen. With the shield installed, further taxiing tests were done and the reflections were completely eliminated. A small amount of reflection still exists in the canopy itself, but their location does not make them objectionable. It was known that the great forces on the control surfaces would require that special attention be given to the hinges. This test ran for 6 weeks in early 1954, and the hinge operated satisfactorily through 2.5 million cycles. This test will determine the effectiveness of the fuel no-air valves in the fuel tanks. It is important when fuel travels from tanks to engines under air pressure that no air travels with it. The valve through which the fuel travels is of new design and restricts the passage of air so that airlocks will not form in the fuel lines. To determine the characteristics of various fuel cells, a series of tests were conducted with models of fuel tanks made in various shapes. The tests, performed in a water tank, provided information as to the availability of fuel at various angles of attack. It showed also the possibility of the center of gravity traveling when the position of the fuel load changes with alterations in the attitude of the aircraft. A great deal of structural testing must be done on various materials and the different methods of joining them. For this purpose, a fairly extensive manufacturing setup has been created to build the variety of panels, cells, fixtures, etc. to be tested to destruction to ensure that the materials and methods used in the aircraft will meet the rigid demands of stress, temperatures, and pressures. Since the specification calls for an aircraft of extreme high speed and high performance, the structure must adequately meet all the requirements placed upon it. These test pieces will help to ensure this. Parallel to the basic development and testing of the CF-105, the preparation for production was well underway in early autumn 1954. Scheme drawings and production loft drawings on glass cloth were being completed as quickly as final design information was made available to the drawing office. The majority of template requirements for master models, tooling, and production will be produced from glass cloth originals, and the drawing of metal lofts will be greatly minimized. The master lofts are produced in the engineering lofting department. Where it is necessary to do any development of detailed parts and flanges, an intermediate glass cloth print is then made for the production lofting department. The glass cloth process, new to Avro, speeds up the production of templates by reason of a contact printing method used for reproduction instead of the necessity of making a photographic negative and from this the full-scale reproduction. When an intermediate is required for use in the production loft, it is made by putting the original in contact with a sheet of light-sensitive glass cloth and exposing the pair in the vacuum contact frame to the light from a pair of heavy-duty arc lamps. When a metal template is required from either a fully developed intermediate or from an original master, it is made in the new loft reproduction shop established in October 1954. The cloth from which the template must be made is measured to determine the size of the dural sheet to be used for the job. The glass cloth is also checked at this point to ensure that all lines are sufficiently strong to give a worthwhile reproduction. This is important if the resulting metal reproduction is to be fully satisfactory. Light-sensitive template emulsion is sprayed onto the metal sheet just prior to making the exposure. After the application of an even coating, the material is placed on the drying table over which is suspended a battery of infrared lamps. The heat lamps quickly dry the emulsion, but since the coating is not sensitive to the infrared end of the spectrum, it is not affected by the light. When the material is dry, it is removed from the drying oven and placed in the vacuum contact printing frame with the required sheet of glass cloth on top of it. With the frame adjusted to the correct position, the arc lamps are then turned on for the exposure. After the exposure, the metal is placed on the developing rack and the developing process carried to completion to produce the required image. The sheet is then washed to remove all of the developing chemicals from it. The templates are stored in racks to dry and thus complete the process. After drying, they are then placed on the elevator, which lifts them to the template shop directly overhead. In the template shop, the production of tools, fixtures, and actual parts for the CF-105 is underway. Completed templates are being used in the production of parts which are cut from flat sheet. The routing operation is guided by the drill and routing template, the pattern for which is the original loft template. When the DRT is assembled with flat sheet and locked with dowels, it is then ready for the routing of a new part. Major steps were also being taken in late 1954 and early 1955 to complete the production master models in the tool and jig shop. Once again, templates are used as a basis for building up the models which are erected on large surface tables. The foundation for the master model of the outer wing is nearing completion, and when finished, will have built onto it a metal skeleton which will eventually be filled with plaster and plastic to make a solid form. Let's follow the process through various steps on the road to completion and use of a master model. Thus we will see how they are made and how they are utilized. The fuselage tank model is at a stage of construction similar to the outer wing, with the foundation for the actual model nearing completion. As these models are completed, a female mold in a series of parts will be made from them. A final male mold is then made from the females to serve as a press or stretch form for contouring skins. The front fuselage model is complete with its web of formers and needs only to have its plaster filling. When the press forms from these models are finished, they will be used in the hydro press or on the Hufford stretch bend machine. The heavy skins required for the aircraft are thus formed. The first of the master models to be completed are several sections of the engine intake tunnel. After the metal framework was finished, the structure was filled with lightweight airfoam plastic, which serves as a foundation for two plaster coats which are applied to the exterior. A rough putty coat of plaster was troweled on over the plastic filler, and finally a smooth finish coat is applied by hand and smoothed out to the required contours. The metal templates used in the erection of the model serve as a guide for arriving at the accurate size and shape, which is of extreme importance. Skins for the duct have been formed on the Hufford machine and sections of duct assembled. The early sections are required for the structural test program, but the forms are a part of the tooling program and are being made ready to produce the required parts for the prototype aircraft. Concurrent with the development of the aircraft itself, the armament groups are preparing for the arming of this all-weather fighter. A CF-100 was being equipped to launch a single missile and perform as a flying test bed to evaluate the general missile launching program. Work on this program, however, was stopped, and further consideration is being given to the missile installation as a result of a firm RCAF decision on the missile to be used. At this time, integration is developing between the armament development and the mock-up programs. A mock-up of a complete functional missile launching package has been installed in the airframe mock-up. This installation has revealed many of the problems involved in the missile package approach to short turnaround time. One of the firms engaged in specialized development work for the CF-105 is Sinclair Radio Laboratories Limited of Toronto, chosen to handle the telecommunication antenna program. Using scale models of the aircraft, antenna patterns are evaluated by illuminating them with radio energy from horn antennas. Sheet metal models have been built to various scales to make measurements of the radiation patterns of the many antennas required. The models are rotated in various planes while the signal detected by a miniature receiver in the model is transmitted to a nearby control booth. An automatic recorder synchronized to the rotating models plots the radiation pattern of the antenna under test. By measuring these patterns in many planes and frequencies, the coverage of communication and navigation antennas in all directions is predicted before the aircraft actually flies. A special test of the radio compass antenna required the construction of this high-voltage electrostatic cage. Integration of the antennas with the airframe necessitated development of specially tailored antennas. The Avro Arrow engineering mock-up is largely of wooden construction and is used for design evaluation. Initially an Arrow 1 mock-up, it has now been modified to embody the features of the Arrow 2 design. The engineering mock-up enables such matters as installation details, clearance, and accessibility to be studied. The mock-up is given a trial fitting with all the equipment the aircraft will finally carry. The electronic system forms a large portion of the equipment installed in the aircraft. Practical trials are made to ensure that, as well as being functionally installed, the equipment is accessible for servicing. The mock-up of the radar package in the radar nose permits demonstration of its rollout features which aid accessibility. Most of the air conditioning and pressurization equipment is located in the fuselage to the rear of the navigator's cockpit. Typical of maintenance procedures developed on the mock-up are engine installation, removal, and servicing using a dummy engine. The weapon pack is designed for missiles, launchers, and missile auxiliaries. It occupies the space between the front fuselage and the engine bay. An external fuel tank is carried beneath the fuselage of the Arrow for long-range ferry operations. The Arrow provides for a two-man crew housed in separate cockpits. The problems of emergency escape from the aircraft have been investigated during tests on the engineering mock-up. After a pilot has made the decision to abandon a supersonic aircraft, there are still human factors that can cause a critical delay before the ejection is completed. This is especially true for an aircraft carrying more than one man. Various seat firing controls and warning systems have been tested, and records made of the time taken for each escape sequence. The wooden mock-up affords a means of checking basic design concepts and for demonstrating principles of operation, layout, and maintenance to Air Force representatives. Fuel system testing is one of the major systems tests which are being conducted parallel with the aerodynamic trials. The rig holds fuselage and left wing tanks, together with all equipment and connections which comprise the fuel system. The test rig can be used to investigate the effects on the fuel system of changes in attitude, temperature, and pressure met under flight conditions, and can simulate engine fuel consumption, pressure refueling, and defueling. The utility hydraulic system, which is separate from the flying control hydraulic system, actuates the landing gear, brakes, speed brakes, steering, and weapon extension. Main and nose undercarriage test rigs are used, individually and in combination, to check raising and lowering of the undercarriage assemblies under a variety of flying conditions. These rigs can simulate structural changes such as those caused by variations of ambient temperature or the thermal effects of high-speed flight. The air conditioning test rig is a complete duplication of the air conditioning equipment carried in the aircraft. To simulate the intake flow of hot air from the engine to the air conditioning system, air from a compressor is heated to 1,000 degrees Fahrenheit. Automatic control of the air supply is maintained and indicated by preset instruments. Other instrumentation records pressures, temperatures, and airflow measurements in various parts of the rig. This aileron and rudder actuator rig was made to investigate the reactions caused by flight loads on vulnerable control areas. Every type of condition which could possibly affect these components can be simulated and analyzed in this way. Here, aircraft bearings are mounted on a bearing test rig to impose loads and to investigate wear. The electrical test panel is used to check the intricate network of electrical components and wiring assemblies which will be fitted in the aircraft. The electrical control of such services as raising and lowering of the undercarriage can be exhaustively tested. Checks such as these ensure that all electrical components and assemblies are fully serviceable when they are installed. A carefully planned and comprehensive test program such as this should reduce costly production delays. Much work has been done in the field of structural testing to ensure correct material specification and design. Here, a magnesium skin stiffened with dural members is undergoing a shear test. Strain gauges on the panel relay information to a 250-channel strain recorder in the test control room. All data is automatically typed for later analysis. To check that the cockpit canopy will operate under various flight conditions, loads are applied to its exterior. The cartridge-operated system is then armed for test. Tests of the canopy system will later be performed on a supersonic sled at one of the United States facilities. In preparation for structural testing on the center section, strain gauges are fitted at various critical positions. Stringent tests are made on all integral tanks prior to installation, as these components undergo heavy pressure loads. To evaluate the efficiency of the flying control system, this rig has been prepared on which it is possible to simulate flight conditions. While loads and stresses applied can be read visually, complete records of tests are automatically made for later analysis. The flight simulator provides a medium for investigating the effect of aerodynamic loads upon the flying control system. A replica of the aircraft cockpit, the installation will register even the most transient controlling movement made by the operator. When the controls are moved, signals are sent to the analog computer. A servo system in the computer equates the various component flight motions and adjusts the cockpit instruments accordingly. Many problems of flight characteristics can thus be solved by anticipating actual flying conditions. Many problems of quantity production can be solved while the first Avro Arrow is still being built. The three-dimensional model layout aids in the utilization of available floor space for efficient manufacture. The floor of the layout is divided into squares, each representing 1 square foot of actual floor space. Such a layout eases planning for the installation of manufacturing equipment and is invaluable in organizing workflow. All models of equipment and aircraft are exactly scaled and are made of plastic, wood, or metal. The operation of ground handling facilities can also be studied in this way. Working experience has shown that this visual planning system simplifies many production problems and gives an overall picture of available facilities. These master models are the key forms for contouring the skins of the aircraft. Skin sections made from production tools are checked for accuracy against the master models, which will form a permanent basis for comparison. The many questions posed by quantity production of the aircraft may be solved on the metal production mock-up. As manufacture of the mock-up continues, important decisions can be made on methods of fabrication, assembly, and work sequence. By anticipation of difficulties, the actual production run in quantity is smoothed as far as possible. The dummy engine in the foreground is used for installation trials in the metal mock-up. Much new equipment has been installed to meet the demands of the Arrow's construction. The new 600-ton press exerts an operating pressure of 15,000 tons and is able to mold much thicker sheets of metal than could the smaller equipment previously used by the company. The 12-inch thick rubber pad presses sheet metal onto prepared forms on the loading table. An unusual feature of the new press is that pressure is exerted from below, forcing the loading table upward into the pad. A hydraulic equalizing device provides for any unbalancing of the loading table, even under maximum pressure. The huge press is very fast, going through its complete cycle of operation in 1 minute. This 200-ton skin milling machine started operations in September of 1956 and is the first of its kind in Canada. Used to machine integral wing skins and stringers from solid metal, this machine is guided by templates and can reach speeds up to 100 inches per minute on straight-through cuts. For conventional milling cuts, this speed can be increased to 160 inches a minute. To heat treat the aircraft sheet metal skins to a workable state, they are loaded into this electric oven. According to the size and thickness of the skins, They are heat treated for varying lengths of time by temperatures in excess of 900 degrees Fahrenheit. When the material reaches the required heat condition, a hydraulic piston lowers the metal sheets into a water tank below. This sudden immersion, which is completed in less than 10 seconds, anneals the skin to a degree which readies them for shaping operations. Extremely high tensile strength must be achieved in the bonding together of metal components. This bonding strength is gained by use of autoclave equipment. Both components are first adhered to each other with bonding material and then wrapped in glass cloth. After this, the assembly is sealed inside a plastic bag which has a vacuum attachment. The air is exhausted from the bag, forming pressure to hold the components in bonding position. The autoclave imposes both the pressure and heat needed for a bonding cure cycle. After the components have been placed in the oven and the door sealed, air pressure is increased to 100 pounds per square inch and the temperature raised to 350 degrees Fahrenheit. On completion of the bonding cycle, the assembly is removed from the autoclave and the now brittle plastic bag can be stripped from the bonded components. The assembly of the first aircraft presented many problems which were solved by the use of new yet simple techniques. The main torque box, comprising a number of integral fuel tanks, is built in a vertical position with the rear spar on top and the main spar underneath to facilitate fabrication. It must therefore be turned round and uprighted in preparation for its entry into the half-wing marry-up jig. Prior to being entered into the half-wing marry-up jig, the forward portion of the half-wing is connected to the torque box along the main spar line. The forward portion incorporates further fuel tanks and the undercarriage bays. When both half-wings are completed, they are removed from their manufacturing jigs and brought forward to the full-wing marry-up jig. At this stage, the wing is almost complete, and it now only remains for both halves to be married up to complete the full inner wing. The center section assembly, which has paralleled the work on wing sections, is raised from its work holder, swung forward, and lowered into a cradle. The left-hand wing is released from its jig, brought forward by the overhead crane to the full wing marry-up, and then manually positioned opposite the right-hand wing. To complete wing marry-up, The two wing portions are connected along the center box. After the addition of the center trailing edge, the full wing is then maneuvered from the assembly jig into the aircraft work holder for final integration with the fuselage and other components. A large portion of the internal services have now been installed in the wing. The center section is then raised for positioning on the fuselage. The fin is next moved from its assembly jig, swung into position, and then attached to the rear fuselage. The next major component to be assembled onto the fuselage is the nose section. Assembly of major components is completed with the installation of the engine bay and the rear fuselage. All Arrow 2 aircraft will be fitted with Orenda Iroquois engines. In the meantime, the first 5 aircraft, designated Arrow 1, will be fitted with Pratt & Whitney J-75 engines. Known to be among the most advanced jet engines available until the Iroquois is in production, the J-75 is suitable for early flight testing and development of the Arrow. The undercarriage can now be assembled. The problem of stowing this component in the space available was overcome by designing the leg to shorten and rotate during retraction. After attaching the undercarriage legs, all their hydraulic and electric services may be coupled to the plane systems. As this first Arrow moves forward to its final assembly point, it signals the approaching advent of first flight. However, before this can come about, there is yet to be completed an intensive program of equipment installation, pre-flight testing, and ground running. The Arrow is the product of years of planning and the emergence of new techniques developed by the close teamwork of Avro's many departments. Their individual tasks combined to produce Canada's first supersonic aircraft. A large number of templates have been made by photographic methods for use in the manufacture of the free flight and wind tunnel models. Many wind tunnel models are being produced, and constant liaison has been maintained between design, photography, and experimental manufacturing, where some models are being built, and Cornell Aeronautical Labs in Buffalo, who manufacture and test. Dimensional accuracy on the templates has been held to plus or minus 1 thou in order to meet the rigid requirements in manufacturing and testing. After preliminary cutting, the templates are filed in an optical filing machine with which the 1 thou wide line can actually be split. This kind of accuracy has been held on both templates and models which have been made at Avro and Cornell. In many cases, dial gauge indicators have been used along with the templates to achieve the required accuracy in the finished components or completed models. The manufacture of the templates and the models is a demanding operation, and the accuracy of the data received from the wind tunnel tests depends entirely on the faithfulness of reproduction of the model from the design. While a great deal of wind tunnel work will be done by NRC in Ottawa, most of the preliminary work has been done at the Cornell Lab in Buffalo. Their supersonic tunnel has provided much data which has proven existing design or shown the need for design changes. Disassembled models were first shipped to Buffalo in June 1954. After unpacking and checking of all components and detail parts, the model is assembled on a sting. This serves as a support for the model and as a pipeline through which passes the umbilical cord used to transmit the information which must be relayed from the model to the control room. One prime example of the value of the wind tunnel has been a design change made in the top lines of the canopy to cure a turbulent condition at the tail, which was indicated in the tunnel tests. When the turbulence was found to exist, tests were carried out in the NRC water tank at Ottawa using a scale model wooden canopy. Progressive changes were made in the shape of the canopy, and the turbulence largely cured. To meet the requirements of the tests, control surfaces at a variety of angles have been manufactured and may be installed on the model to determine the varying effects under changed conditions or attitudes. At this point, the sting with the model fully assembled on it is carried into the tunnel for erection in the test area. When the assembly is fully installed in position and all electrical connections are completed, the tunnel entrance is completely closed and all operations carried on from the control center. In every phase of development, the test program has been particularly vigorous so that when we eventually do get to the production stage, most of the design problems will have been sorted out without having to resort to an excessively long test and modification program on the prototypes. Complete control of all conditions is achieved, and the recording of all results is made in the control room. The control room engineers may change the conditions affecting the model at any time. They can, by means of television, observe the model undergoing testing, and they can directly see the result of the tests on various gauges and meters. The interpretation of the figures is done by the aerodynamics people, and the information is passed to the design and stress offices. They incorporate the required set of conditions or changes into the design and stress specifications. So far, 5 wind tunnel programs have been conducted at Cornell. Many more will be required. Most of the aerodynamics tests are carried out in a Canadian government wind tunnel at Ottawa. Flutter analysis of the Arrow presented several problems that could only be adequately solved by the building and testing of a scale stiffness model to afford a practical check against theoretical calculations. Air is forced into the tunnel and the control stick is pulled back to effect a takeoff. Action of the control stick moves small auxiliary flaps which trim the model during flight. The model tilts up, obtains lift, and flies off its bottom support into the center of the tunnel. Avro commenced a spinning test program in January 1957. These tests discover what conditions will cause the aircraft to go into a spin and what control actions must be made by the pilot to recover normal flight. The dynamic scale model is launched with an initial rotation into the vertical airstream. Scaled to 1/24th size, the model contains a magnetically operated remote control mechanism for movement of the rudder and ailerons, pilot orientation and design information for an anti-spin parachute are other questions to be answered in further spinning tests. Scale models of the Sparrow 2 missile were made to investigate the proposed jettison procedure of the aircraft armament. The tests examined interference behavior of the missiles while being jettisoned under various level flight conditions. The dynamic models were released from their mountings below a scaled aircraft in the wind tunnel. Aerodynamic and jettison characteristics of the externally mounted long-range fuel tank were also determined in the wind tunnel. Models of the drop tank installation have been prepared in different weights to meet the various requirements for wind tunnel testing of these characteristics at different altitudes. The drop tank's airflow behavior is learned from study of filmed records. The Free Flight Model program consists of building a series of 1/8 scale models designed to be released from a ground launching platform with the aid of a rocket booster. The models are made of magnesium and most of the major parts are castings. Wooden patterns were made in the experimental manufacturing shops with the aid of photo templates to achieve the desired lines. A long, careful process is necessary to keep the tolerance within 5 thou. This accuracy has been maintained throughout the Free Flight Model Building Program, which carried on through the summer and fall of 1954. It was originally intended that light alloy castings be used for the wing, and a number of attempts were made in this direction. It was found, however, that the resulting castings were badly sprung out of shape, and time would not permit a solution to be found to this difficulty. For that reason, it has been necessary to resort to a completely fabricated job made in many parts and assembled to form the required delta-shaped wing. We have seen how the original design philosophy has been interpreted into wind tunnel models, which in turn have dictated change requirements in subsequent versions. These changes, as they are recognized, are incorporated also in the free flight models. We have seen, too, how the accuracy of the data from wind tunnel testing depends on the skill with which the models are manufactured. So, too, does the data we hope to get from the free flight of these 1/8 scale models depend on the men who make the patterns and the castings and those who do the finishing and assembling. When the free flight models are flown, they will be boosted away from the launching platform by a Nike rocket, which will accelerate the combination to a speed of Mach 1.9. At this point, the booster will fall free and the model will coast. An extensive array of electronic gear installed in the model will record and transmit the necessary information to the telemetry installation on the ground. Prior to the flight of the actual models, a series of crude models are being launched. These are also 1/8 scale, but they are relatively rough and inexpensive. They have laminated wings of wood and steel with a steel fuselage containing ballast in the nose. They contain electronics similar to that in the final models, and their flight will provide much of the background information which will be required in order to conduct an efficient program of launchings. With the crude models, we will gather much valuable information regarding launching technique, and separation of the booster model assembly from the launcher, the Avro launching platform itself, and the separation of the booster from the model will be proven. The performance of the telemetry setup will be indicated, and the electronic installation in the model will be proven satisfactory or otherwise. The checking out of the transmitter is completed in the experimental hangar to ensure that any effect on the model will be accurately transmitted so that a record may be made. This transmitted record will be the only one available since the model cannot be recovered after flight. The launching program got underway at Point Peter Range near Picton in December 1954. At that time, 2 of the crude models were released. The model and its booster rocket were first assembled and installed on the ramp of the launching platform. This was completed in the assembly shed, and the unit then moved to the launching site. Complete instrumentation was done to ensure that each unknown could be recorded in some way as the model flew at tremendous speed through space. Special cameras were set up at many vantage points to provide a visual record of the flight and to assist in plotting acceleration, speed, and direction. A radar tracking system was set up as an additional means of recording the flight performance. High-speed cameras were set up to record the action taking place at the moment the model and booster would leave the platform. If anything was going to go wrong at this stage, we would want an accurate picture which would help to tell us why. The ramp of the platform was elevated to an angle of 47 degrees for takeoff, and the whole platform leveled at the launching site in the final stages of make-ready for the first launching of a crewed free-flight model of the CF-105. Kinetheodolite cameras were installed in 5 locations to track the models and provide results which, with triangulation, show the velocity and acceleration. This information, along with the telemetry figures, gives us an accurate picture of the behavior of the model. The model and booster assembly, installed on the launching platform ramp, are completely checked out at the launching site and all final preparations completed just prior to the launching of each model. The model-booster combination leaves the zero-length launching platform and accelerates to Mach 1.9, at which time separation takes place and the model continues to coast. The accuracy of the design data and the calculations relative to this phase of the design program were proven to be quite good with the first 2 launchings. In the summer of 1955, final preparations were completed prior to shipping the first drag model to the Point Peter Range. It was swung in this way to provide weight and balance figures which would be related to the records we would obtain in order to show drag and other flight characteristics. Investigations had been conducted with the use of area rule to determine the drag of the aircraft, and we found with the flight of these models that our experimental results were in close agreement with theoretical calculations. Throughout the program, the free-flight models have been changed as necessary to incorporate the changes in the original design which have been dictated by the results of wind tunnel tests of the scale models. The progress in the design as a result of information so gained is exemplified by these views of free-flight models prepared before and after design changes incorporated as a result of investigation of the effects of area rule. All flights of the models are recorded in minute detail by a telemetry unit in order that a maximum amount of information may be obtained from each launching. Of the 4 models seen here, 2 are models for measuring drag and 2 are used for checking directional stability. The latest available resources of many sciences are represented in the extensive and intricate recording and computing apparatus employed to note and to evaluate the information transmitted from the free flight models. Here, the instruments used for transmitting information from the models are being calibrated on a centrifuge under high acceleration conditions. In addition to the firings which have been carried out at the Cardi Range at Point Peter, 2 firings have been carried out at Langley Field, Virginia, the facility of the National Advisory Committee for Aeronautics. The evaluation of drag in free flight models requires a very extensive instrumentation of the range, which was not available at Point Peter at that time. The Virginia facility was also equipped with Doppler radar installations which are capable of high precision tracking of models in flight. The model and booster assembly installed on the launching platform ramp are completely checked out at the launching site, final preparations being completed immediately prior to the launching. After the model and booster assembly is mounted on the launching platform, the ramp is then raised to the launching position, an angle of 45 degrees. The model booster combination leaves the zero-length launching platform and accelerates to Mach 1.8 approximately, at which speed separation of the model and booster takes place. The model then continues in free flight. Concluding the program, model number 11 was fired on January 10th, 1957. The free flight model program proved to be a successful and relatively inexpensive method of obtaining the required drag and lateral and longitudinal stability data. Analysis of this data verified original prediction and helped to ensure the success of the Avro CF-105.